Hello students, today we're going to review properties of water and intermolecular forces. This is going to be a very important topic for us as we proceed in biochemistry because it's going to explain the structure of important biochemical molecules and also how they interact with each other. And so one of the themes that we're going to see is that structure affects what the function of molecules are. So we really need to have a good understanding of the structure of molecules. So there's three types of intermolecular forces that we're going to start off with. Those are van der Waals forces, also known as London dispersion forces. Your textbook refers to them as van der Waals. I mostly talk about them as London dispersion forces, so I'll use both terms. The other type of interactions will be dipole-dipole interactions and then hydrogen bonding. So let's go ahead and talk about how we would recognize what kinds of forces molecules would have and why they are important. So van der Waals interactions are the idea that when you have electrons in a molecule, those electrons are not in a fixed position. So I'm going to draw a picture of, let's say, I don't know, something like methane gas, CH4. Recall from your previous chemistry that it was a tetrahedral molecule. Okay, now picture that it is next to or near another methane molecule. Okay, so we have these Lewis dots with the geometry showing. The electrons are not stationed in one spot. We use these types of Lewis dots to help us to visualize, but they are simplifications of bonding. If you recall from your previous courses that bonding occurs in orbitals, electrons have wave properties. They are very complicated, right? Electrons are complicated. So what we want to picture is we use these types of structures and Lewis dot structures to talk about the arrangement of atoms. But at any given moment, these electrons really are within these orbitals and there's motion and movement. So at any given moment, we could see electrons on one side of the molecule. Boy, that was a really strangely drawn E. I'll redo. Okay, I don't know if that one's any better, but there are electrons. The electron cloud is on this side. Well, if you think about what's going on there, that is what's called an instantaneous dipole. Meaning that at any given moment, electron motion produces one side of the molecule that's a little more negative than the other side. Okay, so the word dipole is going to come up for us. A dipole will mean that one side is more negative than another side of the molecule. Now think about what's that going to do to electrons in the neighboring molecule. Well, they're going to want to shift. They're going to move. So this end of the molecule becomes more partially positive, and this end becomes partially negative. And that's going to create a temporary attraction that I'm going to show with the dashes. So this instantaneous dipole will cause a dipole in the neighboring molecule, and that's an induced dipole. This occurs because of electrons being in motion, and it's temporary based on that movement. And so this type of interaction instantaneous dipole, induced dipole. Well, that's really hard to reference because it's a mouthful. So those are what we call van der Waals interactions or attractions. So van der Waals are instantaneous dipole, induced dipole interactions. These are intermolecular forces because it's the attraction between molecules. I'm not talking about the bonds themselves. So here I'm highlighting a covalent bond. I'm not talking about that. I'm talking about the attraction between two molecules. So the distribution of electric charge around an atom changes. There's motion that creates an instantaneous dipole, which then creates in another molecule an induced dipole. And we call that those van der Waals attraction or London dispersion forces. Now, they are temporary. And because they're temporary, they tend to be initially known as fairly weak interactions. But let's really think about that, and it's going to lead to the next slide, is van der Waals will occur in all molecules because all molecules have electrons, right, that are in motion. But what will determine the strength? Take a moment to think about that. If you want to pause me, you can. But what determines their strength is the number of electrons. So the greater the molar mass, the greater the van der Waals forces strength. That makes sense because the greater the molar mass, the higher the number of electrons, right, that can shift around. So at first, it would appear that these are weak forces, but when you get macromolecules like the ones we're going to talk about in biochemistry, van der Waals forces actually become very strong. So later, let's say we're talking about lipids or nonpolar, lipids that are nonpolar molecules. These would actually be, because those structures are so large, strong interactions. So the other important part here, all molecules have intermolecular forces. All molecules have these van der Waals forces because they all have electrons. But these will be the only forces that you see in nonpolar molecules. Can I write IMF, intermolecular forces? So these are the only forces in nonpolar molecules. Now, let's think about your previous chemistry. What kinds of molecules are nonpolar? And hopefully you remember from your OChem that hydrocarbons. So hydrocarbons are going to be something that you need to recognize, right, in this course. So things like CH4, C2H6, okay, C3H8. You know, these long carbon chains, these will only have van der Waals forces, right, between those molecules. Why is that? It has to do with their molecular geometries. So going back to CH4 as our example, this is a tetrahedral shape. The CH bonds are very, there's very little difference in how those bonds pull. So if you recall in CH4, the difference in electronegativity is small. Now, let me just make sure that you remember what I mean by electronegativity. Remember, electronegativity is the pull an atom has on electrons in a bond. And if you recall from your previous chemistry, the most electronegative atom is fluorine. You don't even need to remember the actual values. You just need to remember that fluorines are most electronegative. And hydrogen's not shown in this comparison, but carbon's a little bit more electronegative than hydrogen. If you want, I can give you the electronegativity numbers for these guys. They're easy to remember because they just go up by 0.5 going across. Hydrogen's is 2.1. So the difference between carbon and hydrogen in terms of pull is very tiny. So it's actually categorized as a non-polar bond. Okay, so with this in mind then, when I look at the tetrahedral structure of methane gas, there is not a net pull of electron density in any direction in that molecule. And so that is considered a non-polar molecule. Okay, because of its tetrahedral geometry, and all the atoms are the same around the carbon. So this is considered nonpolar. When they're nonpolar, then the strongest force they're going to have is van der Waals. Okay, other geometries that lead to this sort of nonpolar structure, do you remember from your chemistry before? You could have another hydrocarbon like the C2H4. It has the trigonal planar shape. That's also nonpolar. There is no net pull in a direction of electrons there. And then lastly, linear shapes with everybody with the same atoms around it. So just hydrogen, nothing different around those carbons. Linear is also nonpolar. So provided that all the atoms are the same around the central atoms, then tetrahedral, trigonal planar, and linear are all nonpolar shapes. They lead to nonpolar molecules, and that leads to having van der Waals as the strongest intermolecular force that these have. Okay. Comparing CH4 to C2H6 to C3H8, if we were to make a prediction on which one would have the strongest van der Waals forces, that would be our C3H8, because the greater the molar mass, the higher the strength of the van der Waals forces. Okay, go to the next one. Okay, dipole-dipole interactions. These are our next type of intermolecular force we're going to talk about. These occur in molecules that have what are called dipole moments. Dipole moments are when you have a net pull of electrons in one direction. So the fancier way of saying that here is an asymmetric internal distribution of charge. They have what's called a dipole moment. Let me show that on this picture down here with CO. If you look, Going back to our electronegativity values from the last page, CNOF, electronegativities increase towards fluorine. Carbon's 2.5, nitrogen's 3.0, 3.5, 4.0 for fluorine. Oxygen is pulling significantly harder than carbon. And so what's going to happen there is that you have a shift. You have a shift towards the oxygen. Okay, and what is shifting? The electrons in that triple bond. So there is a region in the CO that is more negative than this other region that is more positive, because you see a shift in electron density. Okay, and that is what's called a dipole moment. A dipole moment's formed or produced when you have a pull of electrons in one direction. Okay, comparing that to our CH4 from the previous slide, here with the CH4, notice there is not any electrons being pulled any way, there isn't one end of this molecule that's more negative than the other. In CO, the O is a lot more negative than the C. And so what is that going to do then is that those molecules are going to attract each other. So picture that you have two of them next to each other, right? They're going to have an attraction for one another. They will align themselves positive to negative. And now this is more permanent than in the van der Waals because of this bonding, it's always that the O is more negative than the carbon. Down here is a picture of the dipole. Please note that this red one is the carbon and this is the oxygen. So the picture's flipped. Okay, so when we draw our arrows for polarity, the arrowhead, this part's on the negative part. And if you can see here, this other part looks like a plus. So that'll face the atom that is more positively charged. Okay. So when you have polar molecules, then you will have a dipole to dipole interaction. Now, please note that CO is linear. The reason why it's polar and it isn't nonpolar is because the atoms are different here. Okay, recall I kind of made a big deal about it in the last slide that for this one here, linear to be nonpolar, the atoms around the carbon had to be the same. It's when you start having different atoms that you have to analyze the molecule by drawing the Lewis dot structure and figuring out if there's a region on it that's more negative than another. So like, for example, HCN, for example, it's linear, but the nitrogen is pulling harder than the carbon. Nitrogen's got a 3.0 electronegativity, carbon's 2.5. And then, so you have a bond dipole pull that way, but then notice what you have here. You have electrons. So right off the bat, this end is more negative than the other end. And for sure, this has a dipole moment. Okay, and so when these align, then this would be attracted to another HCN molecule in this way, where the N would align with the H on the other molecule. Okay, so polar molecules like CO and HCN, they have van der Waals forces. All molecules have van der Waals forces. But in addition to that, they have dipole to dipole attractions. And so that's going to make them have an extra intermolecular force. It's going to make them attracted to each other more. Okay, so that's the dipole-dipoles. Okay, water is a great example of hydrogen bonding. Hydrogen bonding is a special case, okay? It's a special case of dipole to dipole interaction. And let's talk about what's so special about water. Water is bent, okay? And as a bent molecule, if you notice right away, you take a look at that structure, you have electrons on one side of it, right? You have electrons on this side. Okay, and so right away, this end of the molecule is more negative than the other end. But there's also the oxygen. Oxygen is very small and electronegative, and it's going to pull the electrons in that bond towards it. So now you have an enhanced effect where the oxygen is very negative compared to the hydrogen. And so now water can interact with itself in a very, very strong way because it has a very strong dipole moment, but also the oxygen's small and very electronegative. So these two water molecules can get very close together. And that's going to create a very strong intermolecular force. And we call that hydrogen bonding. Now, a couple things. Hydrogen bonding is an attraction or intermolecular force. It's a shame that it included the word bonding because we're not talking about the OH bonds. Those are covalent. That's a separate discussion. We're talking about the attraction between two water molecules. Okay. The criteria for hydrogen bonding then is that you have to have hydrogen, but there's also another important criteria that it has to have a small electronegative atom. So there's only three that fit this criteria: OH, NH, and FH. And in biochemistry, the ones that are the most important for us, because we see them a lot more, is OH and NH. Okay, so we're going to see a lot of those. Those, when you see a molecule with OH and NH, that means that it can do hydrogen bonding. Okay, there will be other atoms that are involved with hydrogen. So like we might see HS, for example, but sulfur is too big to have such a strong effect. So this one would just qualify as dipole-dipole. These three are capable of hydrogen bonding. Okay, there's other things too that are important. A hydrogen bond donor would be like water or anything with an OH that can donate or be involved in a hydrogen bond. And then there's other polar molecules that can interact with it and accept that and have an interaction. So like this is showing a carbonyl group. Okay. All right, so to summarize then, something like water has van der Waals forces. It also is dipole-dipole because it's polar, but it has sort of this elevated level of dipole-dipole called hydrogen bonding because the interaction of OH as a small electronegative atom makes for a much stronger intermolecular force. Okay, so this is saying exactly what I said, and just has it more written out, is that most often we see a small electronegative atom, such as nitrogen and oxygen, involved in hydrogen bonding. So we're going to see a lot of hydrogen bonding from proteins to DNA, and it's going to be something that you should easily recognize. This is showing an alpha helix structure within a protein, and it's going to be able, it's a way that helps keep this three-dimensional structure. So you're going to see hydrogen bonding between the OH of one group with interacting with, let's say, NHs or carbonyl groups. But we'll come back to this one. But this is just showing you why it's important, is that later we're going to see all sorts of hydrogen bonding in proteins, DNA, and important biochemical structures. Here's a prettier picture of water with its Lewis dot. Notice up at the top in red are the sp3 orbitals where those electrons are. And up at the top of that is where you have a negative, partially negative charge. So that's because of its geometry. So keep in mind that the fact that water has a dipole is because it's bent. Another one that I'm going to just put over here on the side that we will need is, do you remember the shape trigonal pyramidal? So trigonal pyramidal also, if we look at, let's say, NH3, up at the top you have a partially negative, and then you have a dipole moving towards that because N is more electronegative than H. So you definitely will have a region up at the top here where it's more negative than the bottom part. So our two geometries that really lend themselves to dipole moments out of the ones that you've learned would be bent and trigonal pyramidal. Now, water is an amazing molecule. The fact that it's polar and the fact that it has a dipole moment means that it has very strong hydrogen bonding capabilities. And this will definitely play a role in its properties. One of them is the following, that when ice freezes, for example, what happens when ice freezes is that it aligns dipole to dipole, and it creates kind of these spaces between a group of molecules. And what does that do is it lowers the density of water solid, is less dense, than the liquid. This is very unusual because most solids are more dense than their liquid form. But it's when water freezes, it forms these kind of structures with these little gaps in it because of the bent shape and the dipole-dipole hydrogen bonding that's going on. And so you end up with a crystal type structure that's less dense than the liquid. Okay. The other thing that it'll have is that these really strong intermolecular forces will make water very difficult to boil. So, for example, here's water. I'll try it again. Picture it in a liquid. So this will be our liquid. Okay, water liquid is very, very attracted to itself. And so we have to heat it to 100 degrees Celsius at 1 atmosphere of pressure to get that water liquid to vaporize into a gas. And that's because these hydrogen bonds, not the real bonds, covalent, the hydrogen bond, the intermolecular force here, that has to break to go from water liquid to water gas. So these guys have to break apart. Heat alone will not break apart the covalent bond. When you heat some water on the stove, you're not going to create oxygen and hydrogen gas. You are going to create water gas. To actually break the covalent bonds, we have to do something more extreme, like run a current of electricity through it, electrolysis. Okay. All right. So kind of recapping then, water's unique properties. When it freezes, because of hydrogen bonding and its shape, water solid's less dense than the liquid. Huge environmental, right? Because when a lake freezes, the aquatic life that lives there can still survive because the ice is floating at the top. Okay. The other thing that this affects, boiling point of water. Takes a lot of heat energy to boil water. Okay. We have to heat it up to 100 degrees Celsius at 1 atmosphere. And if you think about this, this might seem very trivial, but it's super important because it takes a lot of energy even just to vaporize water to a gas, which is why the Earth has water liquid. Based on its van der Waals forces, if water just had van der Waals, it would boil more like methane gas, which is like negative 262. Our planet would just have gas phase water. But our planet, the way we evolved in life, is because of water liquid, and that's because the Earth has liquid water because of these strong intermolecular forces. So it's all traced back to this one simple diagram up here at the top. The fact that water's bent, it's polar, has a dipole moment, means that it's very difficult to vaporize and boil water. So here's the, I actually misspoke on my boiling point there. Here's the methane. Oh, I'm sorry on that. That's okay. So here's the boiling point of methane, negative 164. I misspoke in the previous slide. The water, look at plus 100 degrees. Okay, but their masses are the same or similar, not exactly the same, 16 and 18. Those masses tell us that methane and water have similar van der Waals forces, but their boiling points are significantly different. So much different that it's amazing, actually. Notice the heat of vaporization. This is the amount of heat energy needed per mole to vaporize. So for 1 mole of water, you almost need 41 kilojoules. For methane, only 8. And what is explaining this? The strong intermolecular forces in water. Okay, the fact that it has hydrogen bonding. Oops, I didn't want to do. it has hydrogen bonding, and CH4 has van der Waals only. Okay. Between water and H2S, it's interesting. If you look, water still has the highest because it has hydrogen bonding. H2S, recall that I mentioned to you that sulfur's too big for such a strong interaction. So that one's only dipole-dipole. And I really love this chart because it gives us a way of visualizing the properties that their intermolecular forces affect. You know, we don't look, maybe you have some water next to you, you don't look over at that water and say, wow, I can see all the hydrogen bonding. But we can see it through its boiling point. The fact that if you want to heat water up, you're going to have to go put it on the stove. You're going to have to put it into the microwave. And it's going to take quite a bit of heat energy to heat it up, and even more to vaporize a large sample. Okay. This was what I was showing you on my less than adequate diagram of water freezing. So this is showing how when water freezes, it forms these sort of gaps, right, between the molecules. So like here, I'll just put a little star. And that is that solid, the lattice structure is becomes less dense than water liquid. Okay, some terms in biochemistry that are going to come up all the time is the term hydrophilic. Hydrophilic means a solute that can dissolve in water. And this is yet another important property of what dissolves in water will depend on its polarity. Okay, water, because it's hydrogen bonding with itself, will dissolve only things that it is attracted to. So what's shown here in that pretty picture, and I'm going to redraw a less than pretty picture, but here's water. Remember, it's partially negative up at the top there. Okay, if I put some, I'm going to use a different color, sodium chloride, which is here. So sodium chloride is a crystal structure. Okay, a tight network of cations and anions. I don't know, I know that you talked about NaCl so much in your previous classes, but just as a reminder that when I look at the formula NaCl, that is a formula unit, Na plus Cl minus, but it's not a molecule because the structure of NaCl is a lattice structure of ions. For every one sodium ion, there are 6 chlorides that surround it. It's not bonds like I'm shown here. I'll draw it like this. They're attracted through a tight ionic bond. And then every chloride has 6 sodiums. So this wonderful graphic here with the green and purple, the green is chloride ions and the sodium ions purple. They're touching each other in an extensive network of ions. That makes that bonding very strong. However, you put it into water, and what will happen is that structure breaks apart, and the sodium ion will be attracted to the oxygen, the partially negative oxygen, and then the chloride is attracted to the hydrogen. And what we have here, what is called an ion dipole. Just as an FYI, a lot of salts, like sodium chloride, will break apart, right, in water, soluble salts, aqueous solutions, to interact with water this way. and energy is released overall when the ion dipole attraction is formed. As a side note, not all solids dissolve in water. So let's say you have magnesium phosphate. That's an insoluble salt. The reason why it's an insoluble salt is because, and I'm racing to get my computer plugged in. The reason why it's an insoluble salt is because, let's look over at the formula, Mg3PO42. The magnesium's 2 plus in charge, phosphate's 3 minus. The attraction there, the crystal lattice attraction, is really strong. And so it will not want to break apart and interact with water. So that's just an FYI, because for us, since we're talking about biochemistry in the bloodstream in the body, we're dealing with soluble salts. There are examples in the body where there are insoluble ones. So like kidney stones is a good example of an insoluble salt that accumulates in the body and can be very painful. But for the most part, we talk about things that dissolve in an aqueous environment. So hydrophilic molecules, things that attract water, will be ions, so you can form ion dipoles. Other things will be alcohols, things that have hydroxyl group. So our alcohol group, carbonyl groups, ester, phosphates, carboxylate groups, ammonium groups. And so these will attract through intermolecular forces with water. And we'll see a lot of examples of these as we go. Hydrophobic molecules will not be attracted to water. So these would be nonpolar, non-ionic. The best example, oil and water. So these would be our friends, the hydrocarbons that you studied a lot in organic chem. So hydrocarbons, when we recognize them as part of a molecule, then we will just automatically say, hey, that won't attract water. Okay, so they have very, very limited solubility in water. This will become a very important discussion later when we talk about fats and why it's so difficult to process fats for energy. And a lot of it has to do with the fact that fats need special carriers to go in the bloodstream. And so that's something that we'll talk about later, but I just want you to realize that hydrophobic versus hydrophilic will be extremely critical when we start looking at biochemical molecules. Okay, so this is going to be something that we look at, solvents that can form clathrate structures that surround nonpolar surfaces. So in the case of lipids, we will come back to this. So I'm not going to say too much about this. Later, we're going to see more specific examples, which I think is just easier to understand when we're applying it. So we'll come back to this idea later. Okay, hydrophobic effect is that nonpolar molecules in solution are going to seek each other out and interact with each other, so that it's going to, they want to stick together to get away from the water, essentially. So here are two nonpolar molecules, and then they're going to come together and interact. That interaction of two nonpolars, so that their attraction is going to be our van der Waals. So they're going to aggregate. Okay. All right. try to minimize their exposure to the water. Almost everything we look at falls into a kind of the gray area, and the gray area are these amphipathic molecules. These have both hydrophobic and hydrophilic properties. So a great example are fatty acids. So a fatty acid has the hydrophobic group. This is our hydrocarbon chain. That's going to be hydrophobic. And then the charged ion, the carboxylate group up here, would be the hydrophilic part. So this would be our COO minus N to it. Okay, this detergent has a sulfate hydrophilic group and then a hydrocarbon chain. Here's a phospholipid. So in biochemistry, we actually deal with molecules that have a part to them that's hydrophobic and a part that's hydrophilic. When you have an amphipathic structure, they tend to form what are called methyl structures. So here, this would be like a fatty acid with a hydrocarbon tail and a polar head. And when they want to get away, or they want their hydrophobic part to kind of clump together, that would be this part here. The hydrophobic tails face each other, and then the polar heads face the water. Okay, and we will talk more about this when we do our section on lipids.